Okay, so sorry to keep you waiting. Again, the title of my talk. This is SRC, a streamable format for generalized web-based 3D data transmission. I'm Max Limper, and I'm from Fraunhofer IGD and TU Darmstadt. So here's the outline of my talk. First, I want to give you a brief motivation of what we are doing, why we're doing it, and then introduce our format itself. I will then discuss the integration into X3D, which can be seen as an example of integrating our container into declarative 3D in general. I will then show some images very briefly from possible applications and mention how they can benefit from our container, and I will conclude with a summary. Okay, so let's come to the motivation. We have found that many web-aligned formats for transmitting 3D mesh data have been developed within the past few years, and I've just listed a few examples here, like the WebGL loader, X3D binary containers, glTF, very popular, and OpenCTM, for example. However, there is still no widely accepted common solution, and all those formats obviously come along with different strengths and weaknesses. And we thought about several points and compared all those formats and extracted some requirements that are, at least for us, important. And I have listed those requirements here, so we have extracted 7 important points for us. The most important point was to have something that allows for direct, in ideal case, zero-copy GPU uploads. So you want to download your data and then directly push it to the GPU in order to avoid any decode overhead, which might become pretty crucial when it comes to mobile devices, for example. And the second point is the ability to have progressive transmission, which is of course very important in a web context. Then, the third important point, we want to decouple the number of downloads, so of HTTP requests that are issued, from the number of draws or the number of meshes in our application. As trivial as this sounds, there are some formats that do not have those 2 points decoupled. So this is very important, especially if you want to build scalable applications with large models. Then, of course, we are all doing declarative 3D here, so X3D, XML3D, declarative 3D solutions. We want our format to be easily integrated into declarative 3D frameworks. And we want to allow some form of data reuse and data compositing, so taking different chunks from different mesh data sets and combining them somehow in your application. This should be easily possible. And the last 2 points, we want to have the possibility to use compression, so different compression methods, simple compression methods like quantization, as used by the X3D formats, but also maybe more sophisticated compression methods that also compress connectivity of triangular meshes, like the TFAN method that has been recently considered by glTF. Then, finally, we want to have the possibility to integrate compressed texture data in what we call GPU-friendly way, and it's basically a very simple approach. Just like for meshes, we want to be able to download the compressed texture data chunks and push them directly to the GPU, without having to decode anything like, for example, JPEG or PNG images. And if we look at the X3DB format and glTF and the X3D formats, for example, and compare them, we will find that the glTF and X3D formats do a pretty good job on most of these points, but not both together. So, for example, in glTF we don't have the possibility to progressively download binary mesh data chunks, and in X3D we don't have this clear separation of the number of downloads and the number of meshes in our application. And of course in X3D we have declarative 3D integration proposed and so on. So what we thought was maybe we can consider both of those formats and take the best of both worlds to build something that fits well with our X3 development efforts and at the same time is general enough to be used in other contexts as well. So the SRC format is a structured header and a binary file body, and SRC stands for Shape Resource Container. So coming from the X3D world, you could say in an SRC you can store everything that you usually store in a shape node, like material, textures, and of course geometry. And we have three words, binary words, pre-header that contain format ID in first word, then version and encoding of our file, so header encoding, and then the length of the header so that we know where to find the binary file body. And we basically allow for various header encodings. Currently we only support JSON because it can be easily evaluated, parsed by the browser. We have adapted some basic concepts from glTF, which were already there. There was no need to reinvent the wheel. However, we have added some very important features. And the first one is progressive transmission. Second is an integration into declarative 3D frameworks via X3D. So we have proposed some X3D nodes, which I will show. We support data compositing via X3D. And we support quantized mesh data. And finally, we support to incorporate compressed texture data into the SRC files, which is not possible with glTF. So, first of all, if you take a look at the layers of glTF, you have the high-level mesh layer, which then contains references to so-called accessors. And those are index and attribute data, usually. And those accessors then use buffer views that each point to exactly one buffer. So what we changed here is that a buffer view does not point to a buffer anymore, but to one or multiple chunks. And those buffer chunks are the basic byte layer. Additionally, we have manipulated the accessor layer, so accessors can now be index views or attribute views, so they are somehow typed. And we have quantization as a basic compression method via two additional attributes that are called decode, offset, and decode scale, and you can use them directly in the shader to denormalize your quantized integer data to the original, ideally, floating point values. So let's take a look at another concept, which is the integration of textures. Similarly to meshes, we allow that there is a high-level object called texture, and one texture does refer to one or multiple texture images. And texture images are again composed of one or multiple chunks. So that's exactly the same chunk layer they are referring to as already used for mesh data. It's just bytes. And the reason why we have this texture image in between is because we want to allow for compressed textures, and it is pretty common to separately transmit the mid pyramid along with the compressed texture, because the mid levels are also compressed, and they can usually not be generated on the fly on the client side that easily, so it's common to transmit them along with the original texture. And this is why we allow here multiple texture images to be contained in one texture. So that's the format, basically. You can see that both mesh and texture map to the same byte chunk at the end. And if you're interested in details, you can, of course, look it up in the paper. Okay. So having this chunk layer allows us to have an interleaved transmission, not only of the mesh data itself, so for example, vertex data and index data in interleaved fashion for progressive transmission, but also of mesh data and texture data. I can show you a small video, very small. That illustrates this for a very simple use case. So this is a video from a web application, and you can see here in the top the amount of kilobytes that has been loaded from the binary file body. And here you can see in yellow how many texture chunks we have loaded. So we have loaded a first texture chunk, a very low resolution texture, and in red you will see when geometry comes in, and then of course the rendered result. So let's continue loading. So at this point we have loaded the first chunk of geometry, and this is using the pop buffer method, by the way, to progressively stream the geometry data. And you can see that one can already recognize what it is, the object, but I think a high resolution texture wouldn't help here, so we are fine with the low resolution version at this point. Then, as soon as new geometry pops in, we can recognize the low resolution texture, so it might be a good idea to load texture data again. So we load the next texture level. And now, again, you can see the blocky artifacts from the pop buffer method, so it might be a good idea to stream more geometry, and then we're done. Okay. So how do we integrate this into X3D? In X3D we have the binary geometry node, and here you can see an example. The binary geometry node is used in the geometry slot of the shape node, as you might know. And what you can see here is that it comes along with a lot of attributes that were added to X3D as field values. And actually, we thought that that might not be the right approach, because when you think about it, a field is usually something the user wants to manipulate, or at least he wants to read it, but we think that the user might not be interested in knowing that the core type is in 16, for example, or which primitive type is used for rendering. He just wants to have geometry and load it and do something with that. So this information, and if you think about glTF, for example, which we used as a very basic starting point for our SRC format, does already contain this information in the header. So we have this in our JSON header, and therefore we can externalize all this information, and this is what remains. So this is our external geometry node, and it simply contains one multi-field with a URL, just like the inline nodes, we can have multiple URLs as fallback, and it just points to the SRC file. Obviously, at that point, other formats could also be used. You could also include a collada file this way, or whatever you like, theoretically. And this allows for much faster parsing of the HTML page, especially if you have a very large model. So this is one benefit, and the other benefit is that it's easier to read, of course. But what we can also do is, because we have some addressing scheme inside our structured JSON header, we have names for all the meshes and textures. We can address them in the X3D scene. So, for example, here you have one SRC file, and this SRC file contains, of course, the header, and then in the binary body data from one mesh, which is entitled mesh 1, then one texture, and then another mesh, which is entitled mesh 2. And you simply refer to those by having the URL for your external geometry nodes here and here, and then a hash separator, which is very similar to HTML, and then the name of the mesh. And similarly, you can use this in an image texture tag to refer to this texture here from the SRC file. So simply use the name that is stored in the JSON header. And by the way, sorry for switching all the time. By the way, this of course allows us to control the number of HTTP requests we have in our application, because we can batch things together and download them in a single file. Okay. I have a short timeline, so we have questions after the training. Okay, thank you. So what we also allow, and I want to show this just very briefly, is some kind of mesh data compositing with a new node which is entitled source. And this is pretty similar what X3D does with Xflow, and we have studied it, and we think this could be a way to integrate something like that into X3D. So as you have seen on the previous slide, we have names for the meshes. So if we load an external geometry node, we already know what names the meshes and also the attributes have. So the source node has a name attribute that tells us, okay, I want to override that attribute that has that name, and the name attribute is specified. And then we have also a URL, and then we can say, okay, we want to have this SRC file, we don't want to have that mesh separated with a hashtag, and then with a dot, we want to have that attribute from the mesh replacing the old attribute with that name. And you can also nest those nodes in order to have recursive overrides. And in that case, the external geometry acts as a kind of top-level source node that consumes all the data in the SRC file. You can read much more about that and the rules that are applied in the paper. Okay, we also have an external shape node. So this node goes even one step further, and it also includes the material information that is stored in the SRC file, like the textures and the material descriptions. And it provides an even smaller HTML layout because you don't need the appearance and material tags and so on. And inherits two additional fields from the X3D bounded node, which are bbox center and bbox size. And by having this bounding box information at hand at the shape node, we can load it on demand. So that's a great advantage. If you have a really large scene, you don't want to load everything right in the beginning, but you need to have some information where something is located in order to load it as soon as it comes into your view raster. So that's the reason why we have this bbox center and bbox size fields inherited here. And yeah, so we can easily load the SRC file on demand. If there's no material data in the SRC header, we have a default definition, so using a default X3D appearance with a default X3D material, which is gray, and then this will be used instead. Okay, so let me now show you some applications or illustrations for possible use cases. As you have seen in the video, the elephant was kind of popping in. I don't have a pop filter here in front of the microphone. With the pop buffer method. And what we did there was interleaving chunks of index data and vertex data and putting these chunks subsequently into respective buffers on the GPU. This is not possible with glTF, for example, this way, because we don't have this chunk layer. And this is one of the major reasons why we needed to have something different that provides progressive transmission. Another application, you might have seen it on the X3D page, is the walkthrough through the Siena Cathedral. if you launch it right now, it's not using the SRC files, the example that is online, and you might see that it takes quite a while to load all the texture data. And in this case, the texture data is much larger than the mesh data in this scene. So the textures are 240 megabytes in PNG format. And if you compress it with ext, you get, of course, some loss, which is, however, we think acceptable. It's also used in games. It's a pretty common compression method for texture data. And you get down to 78 megabytes, which is already great for transmission. But then the other advantage is that you can directly push this data to the GPU and use it for rendering without having any decode step in between, which you have for the PNG image. So you do not only save transmission time, but also decode time for a very slight loss of quality, which is tolerable in very most cases, we think. And then finally, one of the most important use cases is CAD visualization. So here are two examples from the automotive and energy sector, and you can also see those at our booth at the SIGGRAPH, which is one of the reasons why I don't show the demos right now. You don't want to see it 5 times in a row or something like that. And in those applications, we have more than 10,000 identifiable objects, and those objects cannot be batched up front because it might happen that an engineer updates a single part. So he just changes something and then presses a button, and that thing gets directly encoded again, and someone else presses F5 and sees the updated version. But in order to have that, we need to keep an eye on the number of downloads, because obviously 10,000 downloads is pretty much. And so the least thing we can do is to have a format that has a joint header and body and not those two separated, like glTF. So it's self-containing, and it can also be used to exchange those files in a very simple manner. And this leads us to only one request per object, in contrast to X3D binary geometry, for example, which has separate files for index data, at least, and attribute data. Also, the size of the HTML page is crucial if we use X3D for these applications. The external shape node definitely helps compared to the binary geometry node with shape, appearance, and material, text, and so on, because then everything single line matters, and the external shape node is probably the most compact thing you could think about in that context. So to give you a summary, SRC stands for Shape Resource Container, and it's a format that contains a structured header and a binary file body. It's a container format for mesh data and textures, and we have shown simple yet flexible integration into X3D as an example of integrating a format into declarative 3D solutions. And if we look at the points I introduced in the beginning, there's one open point. For compression, we have provided the decode offset decode scale attributes, but that's the only kind of compression we currently have. We only have quantization of attributes, and we do not provide any other sophisticated connectivity compression methods or something like that at the moment, but this would be an interesting point for future work. Okay, so thanks a lot for your attention, and I'm now very open to questions.
There's time for a couple questions if anybody has any.
I think Michael already had a question during your talk. Okay. Yeah, I mean, the inline mode is usually.
Can you repeat the question?
Yeah, okay. The question was why we don't use the inline node, but the inline node has its place in the scene, and it includes a sub-scene. And for example, you could use the inline node next to a group node to include a completely different scene, but you could not use it inside a shape node. So that wouldn't be valid X3D, I think. Yes, Mike.
There are other content things that are large, like interpolators. Are you thinking of doing similar sort of containers for other parts of the scene graph? They can be really big.
To be honest, animation data is something we haven't considered yet. So this might be also a point for future work. Yes.
Okay, so I really like the development with shape and everything. I saw the sentence in Explode. Just a few questions to that. You said it's possible to replace individual buffers for measures. You gave this example where you replace the color of the duck. And how does this work if external shape actually consists of several meshes? You just want to replace the color of one of these meshes. Is that possible?
Yeah. External shape and source node, those two working together, is an open problem. We don't have investigated it yet, finally, to have a clean solution with a well-defined set of rules. We have that for the external geometry node. So you can find it in the paper. So for the external geometry node, it's pretty clear, but for the external shape nodes, which should, we think, be able to include multiple meshes, we are not having a schema yet.
And how does this work when updating data that is linked inside? For instance, you know, modify the color that's linked to this external geometry. How can you use this?
You mean you change it inside the SRC file?
You have JavaScript. So you have a JavaScript program that continuously modifies the color that's essentially hooked up to how can you use this?
This is not a use case we have considered, because like the X3D binary geometry node, for example, we are just interested in static data. We are not interested in data that should be manipulated at runtime. It's the same for X3D binary geometry, for example. I mean, yeah, you could imagine some generic way to access your shape and then the geometry and then the positions or whatever, independent of what kind of container you use to load your geometry data, but that's out of scope. So we have just considered static data, like the X3D containers, like binary geometry, image geometry, and so on. It's all static.
Well, I have to say it's very similar to the ideas we had on our paper that we presented in session.
Yeah, I'm really looking forward to it.
Okay, thank you very much, Max.
Thank you.